In this lesson, we're going to talk about parent graphs. So we start with a linear equation. And so remember, to graph a linear equation, you need at least 2 points. I'm going to use 3 for these examples. So in the first one, we have y equals negative 3x plus 1. So you pick 3 values of x. They could be any values that you want. So I usually pick easy numbers like negative 1, 0, and 1. You plug in each of those numbers into this equation to compute what y is. And so when x is negative 1, y is 4. When x is 0, y is 1. Remember, that's a special point called the y-intercept. Um, and when x is 1, y is negative 2. Each of those 3 points get plotted on this graph. So negative 1, 4 is here, 0, 1 is here, and 1, negative 2 is here. Remember, those 3 points are what we consider to be collinear. You connect the points and you have your graph. We put arrows at the end of the line because this line actually goes on forever in both directions. Remember that the domain of a linear function of the form y equals mx plus b is all real numbers. This also falls under the category of a polynomial function. It's just a special type of polynomial function. The next example is y equals 2/3 x. Here, because my coefficient in front of x is a fraction, to make it easier on me, I picked numbers that will result in y values that are integers. So I picked multiples of 3 as well as 0. So I have negative 3, 0, and 3. When you plug in negative 3, you get negative 2 as your y value. When you plug in 0, you get 0. And when you plug in 3, you get 2. So 0, 0 is both a y-intercept as well as an x-intercept. It's where it's where the two axes intersect. It's the origin. Negative 3, negative 2 is down here, and 3, 2 is up here. Again, connect those 3 collinear points, and you have the graph of a line. And just as a reminder, when the number that's multiplied by x is negative, that is considered to be the slope of the line. Your line will be going downward from left to right. But when the number that's multiplied by x is positive, again, that means it's a positive slope, your line will be going upward from left to right. Okay, so there we have 2 examples of the graph of a linear function. This one is also the graph of a line, but this is a special type of situation. This is a horizontal line. And so when your line is horizontal, the y values will always be negative 2 in this example. And your x's could be anything you want them to be. So again, I picked 3 easy numbers, negative 1, 0, and 1. So when you graph that, you'll have negative 1, negative 2, 0, negative 2, that's also the y-intercept, and 1, negative 2. Connect those 3 points, and there we have our horizontal line, which represents the graph of y equal negative 2. And this example is also the graph of a line, but this is a vertical line where the x-coordinates are always 3. And your y's could be anything you want them to be. So I just picked 3 random values of y. Negative 2, 0, and 1. So 3, negative 2 is here. 3, 0 is here. That is the x-intercept because it's where it crosses the x-axis. And 3, 1 is here. Connect those 3 points and there is your vertical line. Remember, you only need 2. 3 is more than enough. And so then you can connect the points of your line. So to graph other types of functions, you usually need more than 2 points. So this next example is a quadratic function because of the second degree here. That makes it quadratic. And the graph of a quadratic function is a parabola, which is written like that. So here I picked several points. And again, x could be anything because this is yet another example of a polynomial function and the domain is all real numbers. So x could be anything you want it to be. So I picked a few negative, 0, and a few positive numbers. And if you plug them in to this, you'll compute the values of y. So your y values are all listed here. So here's negative 3, 5. Here's negative 2, 0. Here is negative 1, negative 3. Here is 0, negative 4. Here is 1, negative 3. Here I have 2, 0, and 3, 5. So 0, negative 4 is both the y-intercept, but it's also considered to be the vertex of this parabola. The points at negative 2, 0, and 2, 0 are considered to be x-intercepts. So connect those points in that U shape and you get the graph of your parabola. The next example is the graph of a radical function. So I have y equals the square root of x minus 2. Here, this is not a polynomial because of the radical. So you do have to worry about the domain of this function because you want to avoid negative numbers inside of the radical because then the result would be an imaginary number. So here, if you recall how we found domain, you take the inside part, you set it equal to 0, and you get x is equal to 2. So 2 is in the domain. And then if you check values to the left and right of 2, if I pick something less than 2, the result inside of this will be negative, which is imaginary. If I pick something greater than 2, the result inside of the radical is positive. So your domain is from 2 to infinity. So anything starting from 2 and anything to the right of 2 are acceptable values of x. So here I picked a few numbers that would be easy for me to take the square root of. So when x is 2, this becomes the square root of 0, which is 0. When x is 6, it becomes the square root of 4, which is 2. And when x is 11, 11 minus 2 is 9. The square root of 9 is 3. So I have 3 points, and the graph is a curve that kind of grows slowly, the way you see here. So here I have 2, 0, 6, 2, and 11, 3. So your x's get bigger much faster than your y's do, which is why the graph increases slowly. So there's the graph of our square root function. Okay, the next example in green is the graph of a rational function. And with rational functions, again, you should check to see if there are any restrictions on the domain. Here the domain is all real numbers except for 1. And that's because you would take the denominator, set it equal to 0. And so I know that x equal to 1, this denominator would be 0, which means it's undefined there. But any other value of x is fine. So that's why it's all real numbers except for 1. So I picked a few numbers. And again, I skipped 1 here just to point out that it's undefined. So you really can't graph that. When you plug in negative 1 in here, you'll have 2 over negative 1 minus 1, which is 2 over negative 2. So that's where we get negative 1 here for y. When you plug in 0, the answer is negative 2. When you plug in 2, the answer is 2. When you plug in 3, your answer is 1. So I have several points to plot. This point, this line at 2 is a vertical line, which is an asymptote. The graph will get close to that vertical line. That's why it's dashed. It's not really part of the graph, but it kind of frames where the rest of the points go. And then the rest I plotted here in purple. And so the graph is really in 2 parts, but this represents the graph of this rational function. And just to remind you, when you have a graph, you can figure out what the range is pretty easily. And so the range here would be all real numbers except for 0. because this part is going towards negative infinity. This part here is going towards positive infinity, but it never quite intersects the x-axis, which is when y is 0. So we'll get really close to it here, and it will get really close to it in this direction, but it's never going to equal, your y will never equal 0. This would be impossible for this to equal 0 unless the numerator is 0, and the numerator is a constant of 2. So the y will never equal 0, which is why your domain is all real numbers except for 0. Okay, so you saw examples of linear equations, a quadratic, a radical function, as well as a rational function. You saw the graphs of all of those. So when you have the graph of a function, you can of any equation, you can figure out if it's a function by doing the vertical line test. And the way it works is the vertical line test is a visual way of determining if a graph represents a function or not. If any vertical line passes through a graph and touches the graph at only one point, then the graph represents a function. If a vertical line passes the graph through more than one point, then it will not be a function. So this goes back to an earlier lesson when I first defined functions for you. I said for every x, there's only one y. And so that would be it only touches the graph at one point. But if there is one x that goes to two different y's, then that means it would be crossing in more than one point, then that would be not a function. So this is just a visual way of representing the definition that was discussed in an earlier lesson. So here we have a few pictures, and we're going to figure out which one is a function and which one is not. So in picture A, if I drew a vertical line anywhere throughout this graph, so if you can imagine like having a ruler and kind of scanning it through, no matter where I am on the graph, I'm only touching this graph at one singular point. And so when that's the case, then you can clearly say that graph A is the graph of a function. But graph B is not. Even though here, yeah, I only touch it once, but once I get to this part of the graph, a single vertical line touches the graph in 3 places. So therefore, it doesn't satisfy this definition. It's touching it at more than one point. It does not represent a function. So part B is the graph of an equation, but it is not a function. And graph C also fails the vertical line test. And that's the way you would state that it fails the vertical line test. So therefore, it is not a function. In this example here, this particular vertical line would touch the graph in 4 points. So again, if it's more than one, if a vertical line touches it anywhere in the graph in more than 1 point, then it is not a function. So that's always a quick way to figure out if something is a function if you have a graph. Okay, so this is when we talk about parent graphs, which is what I mentioned earlier. So they are common graphs that are used in this course and future courses that could look exactly the way I'm going to represent them, but they also could be manipulated in some way. They could be shifted to a different part of the graph, or they might be skinnier or wider, depending on what's done to them. But recognizing the parent graph is very important in order to transition into different variations of it. So I want you to become familiar with these, memorize them, and recognize them so that when they're used in the future, you're familiar with them already. So the first parent graph is the graph of a line, and this is the most basic of your lines, y equals x. It looks exactly the way as seen here in this blue. It crosses the origin. So that's our linear function. And remember, linear functions fall under the umbrella of polynomials. So the domain for this line is all real numbers. And if you read the graph, this part is going towards negative infinity, and then it grows and grows and grows forever. This part goes towards positive infinity. So your range is also all real numbers. The next common graph is this one here on the right, which is that of a quadratic function. This is the most basic of your parabolas. So y equals x squared, where your vertex is at the origin at 0, 0, and it faces upward again because the leading coefficient here is 1, right? Y equals 1 x squared. When the number in front of the x squared is positive, you'll have a typical U shape. If it was negative x squared, then it would be upside down. It would look just like this, but it would be upside down. So quadratics also fall within the umbrella of polynomial functions, so the domain is all real numbers. There are no restrictions on what x can be, but when you read the graph from bottom to top, the first value of y on the graph is 0, and then it grows from here and there, so it's from 0 to infinity, including 0. So you should memorize that the vertex here is at 0, 0, but if you don't remember or if it looks a little different than what I stated here in the future, remember this is the formula to compute the vertex of a parabola. The x-coordinate is negative b over 2a. The y-coordinate is the function value at negative b over 2a. So that's the way to compute the vertex for any type of quadratic function. Okay, then we go on to other parent graphs. This one here on the left is a cubic function, y equals x cubed. This is also a polynomial. So therefore the domain is all real numbers. And it looks like this, like kind of stretched out S shape. It increases from left to right. And if you read the y values, this goes towards negative infinity and then it increases. And this part goes towards infinity. So the domain and the range are both all real numbers. Okay, now we go here to the right. This is the graph of the square root function, y equals square root of x. We graphed the square root, a type of square root function earlier, but this is the parent graph, just root x. Remember, there are restrictions on the domain. And so x can be 0 and x can be a positive number, but x cannot be negative because if I plug in a negative number in here, like let's say the square root of negative 9, that would give me an imaginary result, and you have to avoid imaginary numbers. So x can be anything from 0 to infinity. So that is your domain. And if you read the graph, the first value of y that this graph takes on is at 0, and then it increases from there. So your domain and your range are from 0 to infinity, including 0, which is why we have a bracket around it. Okay, now we get to the one here on the left. This is called the absolute value function. The absolute value function looks like a V. It looks like two lines that are connected at this corner. And the corner for absolute value of x is at 0, 0. So when x is 0, y is 0. And any negative numbers that get plugged in will turn positive, which is why everything is above the x-axis. And any positive numbers stay positive. So everything will be in quadrants 1 and 2, except for the corner, which is on the x and y axis. It's at 0, 0. So there are several points plotted here. Remember, an absolute value changes negatives to positives, but positives stay as positive. So again, although this is not a polynomial, the domain is all real numbers. X can be anything, positive, negative, 0, a fraction or a decimal, anything. But your range, when you read this from bottom to top, is from 0, and then it increases to infinity. So there will never be anything below the x-axis, which is why there are no negative y values on this graph. Okay, and the last one is a type of rational function, and it has a special name. It's called the reciprocal function. Like I said, it's a type of rational function. And with these are a little bit more complicated because they will often have restrictions on domain as well as asymptotes. And remember, an asymptote is just a line that the graph approaches but doesn't quite touch. And this one has both vertical and horizontal asymptotes. So let's talk about the domain first. The value of x here can be anything except for 0, because if I plug in 0, this is undefined. It doesn't have a numerical value, so there is no y value that I can compute. So my domain is all real numbers except for 0. So you write that in two separate intervals with a union symbol in between. And if you read the graph, the range is the same as the domain because this part goes towards negative infinity. Then it goes up, it increases. This is getting closer and closer to a y value of 0, but it's never going to quite equal 0. This part, it gets close to 0, but then it grows towards infinity. So your range is all real numbers except for 0. So now let's talk about the asymptotes. So there is a vertical asymptote, which is actually your y-axis. This is getting really close to the y-axis, and so is this. So your vertical asymptote is the line x equal to 0. X equal to 0 is the y-axis. So when you're on the y-axis, all of your x values are 0. And there's also a horizontal asymptote because this part of the graph is getting closer and closer to the x-axis, and so is this one. So the horizontal asymptote is the line y equal to 0, which is the x-axis. So again, anything on this x-axis, your y values would equal 0, which is why it's stated as y equals 0. Okay, so those are all of the parent graphs for now. Later in the course, we'll talk about exponential and logarithmic parent graphs that you should be familiar with. But for now, the 6 that I just discussed, you should become very familiar with and understand: domain, range, and in this case, your asymptotes. All the others don't have asymptotes. Okay, so we're going to use those parent graphs in order to sketch a piecewise function. So this is a piecewise function. It is a combination of the reciprocal function and a parabola. So I want to show the reciprocal function for values of x less than 0, but the parabola for values of x greater than or equal to 0. So the left side of this is the purple graph. That's this piece, because I only want for values of x less than 0. And the second part is the part in green. That's the parabola, but again, it's only half of the parabola. So it's not the whole u, it's only for values of x greater than or equal to 0. Because it's greater than or equal to, I have a solid point here. You color it in. Don't leave it open. So now that we have the graph, we can answer this next part, which is what is the domain and range? So the domain is going to be all real numbers. This part are all negative numbers, and this part is all positive numbers, including 0. So there's nothing missing. So that's how we express it with interval notation. And the second part, this is how we express it with set builder notation. It's the set of all x such that x is an element of the real numbers. And if I read my range, this goes towards negative infinity all the way up to 0. Doesn't look like it's quite touching 0, but then here it equals 0, and then it goes to infinity. So basically, every real number is accounted for, all the negatives, 0, as well as all the positives. So for your range, there are no restrictions. It's just all real numbers. Okay, here's another piecewise function. This time I have 3 parts. I have g of x is equal to the absolute value of x. Remember, absolute value looks like a v, but I only need to show it less than or equal to 0. That's this part, this line that's on the left side of the graph. Square root of x, that's a square root function, but I only need to show it between 0 and 4. So when x is 0, y is 0. When x is 4, y is 2. So that's that curve in in blue in the first quadrant. And the last part of my piecewise function is g of x equals -2. That's only true for values of x greater than 4. So I put an open circle here, and then I draw a line going to the left. Okay, so there's my piecewise function. My domain is, again, all real numbers. This is all my negative numbers and 0. These are all the numbers between 0 and 4, including 4, and these are all the numbers greater than 4. There's nothing missing. So it's all real numbers. And my range, when I read this from bottom to top, the first value it's going to take on is -2. But then there's like a gap from -2 up to here. It's missing. So then it starts again from 0 to infinity. So it's kind of an unusual way to write it because I have a single number, -2. You use kind of the curly brackets there. So it's -2 union the interval from 0 to infinity. And this is the way it would be represented in set builder notation. It would be y equals -2, or y could be greater than or equal to 0. So those are the two values or possible values of y in this piecewise function. Okay, so now we go on to number 3. I have h of x is equal to -x squared for values of x less than 0. It's equal to 3 for values of x between 0 and 2, and x minus 4 for values of x greater than or equal to 0. -x squared is the upside down parabola, so this is this part. We have an open circle here because it's just less than. This part is just a constant. They're all less than symbols, not less than or equal to. So again, open circle here at 0, 3, an open circle here at 2, 3, and then you connect to that horizontal line in between. And the last part is a line. This is a linear function. You need 2 points to graph a line, so you definitely need to start at 2. So when x is 2, y is -2, and that's closed because it's greater than or equal to. And then I plugged in another number greater than 2, like 4. And so I get 4, 0. Connect those 2 points going to the right, and there is your line. Okay, so there we have it. There's our graph. Our domain is all real numbers except for 0, because these are negative numbers. This is between 0 and 2, not including 2. So when x is 0, there are no y values. Both of those points are open. So it's all real numbers except for 0, but your domain, this part goes from -infinity. Here it's undefined, but here your y is equal to 0, and then this part goes on and on forever to infinity. So no restrictions on the domain for this graph. So you need a good graph, and then be able to read things carefully to answer your questions regarding domain and range. All right, there are graphing calculators that can help you to graph in the future. These are instructions for these specific Texas Instrument models, Texas Instrument 83, 84, or 86. If you have a different calculator, there's lots of resources online to help you figure that out. So these are the steps that you would have to follow in order to enter a function into a graphing calculator, and it will give you a picture. But you could also use apps. There are lots of free apps. So I use Desmos. That's an app that you can download, or you can go directly to their website, and that's very user friendly. So this is an example of something that I entered into Desmos. Y equals x cubed minus x squared plus 1. And when I do that, I get this picture. So this is a third degree polynomial. And so you'll be able to see some points on this graph. So it works very nicely. So you should probably get familiar with that one. So here's one for you to try. It's sketch the piecewise function, state the domain and range in both interval and set builder notation. These are two of the parent graphs that I gave you earlier. But again, always pay attention to what the restrictions are here. Okay, so that's it for this lesson. Good luck.